So welcome to this new IFIMAC colloquium. It is my pleasure to present you our speaker today. Is Javier García de Abajo, who is an ICREA research professor and is the leader of the Nanophotonics theory group at the Instituto de Ciencias Fotónicas, ICFO, in Barcelona. A little bit of his bio. In 1993, he obtained his PhD in condensed matter theory from la Universidad del País Vasco. And after that, he went to Berkeley National Lab, where he spent 3 years. Then he came here to Madrid, where he became a staff scientist and a research professor in 2008. Then in 2013, he moved to ICFO, where he is now. And his interests range from, of course, electron microscopy, light matter interactions, quantum optics, condensed matter physics, ultrafast phenomena, and nanophotonics. A lot of topics. And his group applies theoretical and computational tools to investigate new phenomena and explore their potential application for technology, such as sensing, imaging, or information processing. He has co-authored more than 400 papers and has received tens of thousands of citations. He is a very influential actor in the topic, in nanophotonics in general. He is currently a fellow of the American Physical Society, the Optical Society of America, and the Electromagnetic Academy. And last year, he was awarded his second advanced ERC grant, which is entitled something like Quantum Enhanced Free Electron Spectral Microscopy, which is closely related to the topic of his talk today, which is quantum nanophotonics with free electrons. So Javier, thank you very much, and the floor is yours.
Okay. So thank you very much for the invitation to come here. It's a real pleasure. And this is top science in Spain. The Autonomous University has always been a reference for all of us. And then quantum, okay. This is not about the quantum fever that we are experiencing now. Quantum information, quantum computing, etc. No, I think there is much more than that in quantum. Hopefully it will survive. Anyway. So then quantum nanophotonics with free electrons. So first of all, I want to show here, if we want to do resolve excitations in energy or in space, something that is relevant is what is the wavelength as a function of energy to compare in space for photons and for electrons, right? And in this range, eventually they cross, no? But in this range, electrons win by far, right? So it's normal that electrons have been used to do microscopy, and there is a long tradition in using electrons for this purpose. And starting from the discovery of the electron, the identification of a wavelength for matter waves, basically the design of magnetic lenses and the first electron microscope. This is the son of the first Thomson, who also received the Nobel laureate for demonstrating that electrons are waves and they behave as waves. They diffract on crystals. And eventually, electron microscopy reached even a resolution of 1 nanometer. That was already in 1945, so it's quite remarkable at that time. Electron holography, so holography was first invented in the context of electrons. And lately, so the resolution has been improved down to less than 1 angstrom, and there are methods for reconstructing in 3D. And there is also the possibility of resolving biological molecules in their natural environment in solution, right? So if you look at the different techniques for doing spatially resolved and energy resolved microscopy, then you have some of them that use light and some of them that use electrons. The ones that use electrons are winning. And there is a long tradition here at the Autonomous University about the scanning time microscopy, right? maybe for photonics this is most sensitive to electronic states and not so much for photonic things because the signals are basically overshadowed by electronic excitations, right? But if you want to, the next candidates are electron beams for cathodoluminescence and electron energy loss spectroscopy, and I will explain what that is. But also recently, there is the possibility of having temporal resolution. In principle, you can start with maybe nanoseconds, even down to tens or hundreds of picoseconds using fast electronics. And in some of these techniques, this is already used. No? Eventually, you have ultra-fast optics, and there's part of why photons are involved in this context with electrons. And then you go down to femtoseconds, more recently down to attoseconds. No? And I hope to convince you even septoseconds, we'll see. So first of all, I'll try to be tutorial because I understand this is a very different subject from many of the ones you are considering here. So a photon, which has a certain momentum and energy. And so the light line in this dispersion diagram. And so we are talking about photons interacting with electrons. And so again, some momentum and energy without relativistic effects. And now one form of interaction is if the electron absorbs the photon, and therefore momentum is conserved, energy is conserved as well, right? So this equation is the same as this. It's just omega in terms of the rest. And the final electron velocity, you can substitute here. So it's very simple maths, and it gives you this. So this relation gives you the frequency and the wave vector of the light that can be absorbed by an electron, right? And so actually, if you are at very, very low energies, like in photonics, compared to, say, mega electron volts or something, this is the momentum of light square, so it's very small. It's something you can neglect, so this is a good approximation. And then you have omega with wave vector parallel to the velocity or anti-parallel or anywhere in between, any angle. The important thing is that there is no overlap, and so no interaction, right? So what's happening is an electron cannot just absorb a photon or emit a photon. You go to the rest frame of the electron and cannot emit a photon. That would violate. There is no Cherenkov in vacuum. But then you have photonics, right? And waveguides. In a waveguide, basically you are outside the light cone, so you have confined modes, and therefore you are in a region where the modes in the dispersion diagram can interact with the region in which the electron is able of absorbing or emitting photons, right? So you have this type of interaction. Now, in which context this is done? Currently, maybe this is going to change in the future, but currently, because people are interested in doing microscopy, this is done in electron microscopes. These are the typical characteristics. So you have transmission electron microscopes with energies from 30 kiloelectron volts to maybe 300 or so, or even more. Secondary electron microscopes where you have lower energies below 50 kiloelectron volts or so, down to maybe 1. This is challenging. Other types of microscopes, photoemission electron microscopes, etc. But there is the range, and so you have electron velocities that are this fraction of the speed of light. In all cases, you are interested in having collimated electrons, so the angles of divergence are going to be very small. Then, as a fraction, the fraction of the energy in the transverse direction is therefore much more than in the longitudinal one. It's just the square of this number. So it can be in the range of EV or sub-EV, right? Very, very small. In all cases, you have an electron source, some optics, some specimen, and then some detector. Then what you detect is, for example, the spectrum of the electron, now with very good resolution, and or the light that is emitted, no? Cathodoluminescence. In the context of photonics, these are the signals that are most interesting. So this is a work in which perhaps the first in which cathodoluminescence was used to probe plasmons in nanostructures and image. So this is just a dipolar plasmon. You can see you just scan the electron beam and collect the signal that is emitted, the photons that are emitted, and then polarize these photons in this direction, you see like a dipolar pattern. If you resolve the photons in wavelength, then you see different peaks corresponding to dipolar, quadrupolar, etc. So you can understand the optical modes of, you can image the optical modes of small structures like this. No? And since then, many things have happened, but let me just show you something that I consider the state of the art in electron energy loss spectroscopy. So this is about what one is capable of doing now. And so the energy resolution is in the few milli-electron volt range. This is going down and down. Few milli-electron volts, meaning 5, 4. I think the record that I heard last was around 2. Sub-angstrom resolution, half an angstrom or so, combined simultaneously. In this study, for example, by Quentin Ramase, what they did was to look at the graphene layer where, with a defect where one of the carbon atoms was substituted by a silicon atom, and they aimed the electron beam at different positions. So at each position, they just recorded the energy loss spectrum, and they saw in this range, milli-electron volt. This is the range of vibrational frequencies, right? In the atomic vibrations in the system, and they saw how the spectra are changing, and basically they correlate with the different photonic density of states, right, at the different positions. So it's just the change in the vibrations in the system due to the presence of this impurity. Okay, and this was done with atomic resolution and with milli-electron volt also energy resolution. This is already more than 10 years old, but it also illustrates how you can map photonic modes. In this case, these are silver nanowires, and you can see theory experiment. It's difficult to tell which one is which, but basically you see dipolar, quadrupolar, etc., different standing waves in these materials. The energy resolution, even over 10 years ago, was already reasonably good. And then I think this is about 100 nanometers or so. So this is like a micron or sub-micron sized object. This is also some more recent result in a collaboration with Peng Gao and Qin Dai from Beijing. So basically this is a layer of boron nitride, hexagonal boron nitride, monolayer. And so what we were looking at here is just the photon polaritons. And then the photon polaritons have a group velocity that is extremely low, and you cannot resolve it really with any other optical technique. This is way too small. And electrons are very handy for this, okay? So it allows you to do that. So these are just some illustration of the state of the art in electron microscopy and how electrons are used to do microscopy using electron spectroscopy, also cathodoluminescence, right? For a long time, we've been inspired by Archie Howie, who was a pioneer in basically the father of a whole generation of electron microscopists in the world, in Cambridge. And then he was always arguing that basically by using light and electrons combined, one should gain something, okay? He was always talking about this. And eventually we published a paper inspired by this idea where we suggested if you have a structure like this illuminated with light, and then you have an electron passing by, the electron can gain energy because it just picks up energy from the optical field. If you could do that, then you win something. What you win is that the energy gain peak will have a certain strength. This will depend, of course, on the strength of the electromagnetic field at the structure. And then if your illumination frequency is tuned to a resonance, the field can be strong, this peak will be large. If the illumination is away from the resonance, this will be small, right? But then the strength of this peak depends on how precisely you can tune the light frequency. Even if your resonance is extremely narrow in energy, you can win a spectral resolution. Even if your electron beam has a spectral resolution that is not so good, for example, 1 ED or so, no? But you can have micro electron volt energy resolution combined with atomic spatial resolution, right? By using these two things. Okay, eventually this was done. It took over a decade for that. These are recent results by the group of Klaus Roppers using some structures from Tobias Kippenberg, this microring resonators. So this is a typical integrated optics structure where you have resonances that are extremely narrow and with a very high quality factor. This is what you see optically just by looking at transmission. Right on resonance, you see a depletion of the light that is transmitted, and the width of the resonance is this much. Now you can also do the same what we were saying before. You have an electron. The electron is interacting with this light, and then depending on the frequency of the light, when the frequency is tuned to this resonance, the interaction is super strong, and you measure electrons. You measure electrons that are transmitted and the spectrum of this electron, and you quantify the strength of the interaction. So by measuring electrons, you still get the same resolution, which is now micro electron volt, right? In this energy range. This is a more versatile version of this, in which you can have, in this case, it's just big spheres that have Mie resonances, so the electric resonators. And in this case, I think this was about 4 micron sphere. You can look at it with EELs and still see these Mie modes, or you can have a look at the catoluminescence that is emitted. So you see these peaks, or you can have this electron energy gain spectra, and then you really see them with the right width. But if you go to even larger spheres, in this case it's about 9 micron sphere. Now the quality factor is much higher. These are electron energy gain spectra. You don't see them with EELs or catoluminescence, okay? But then with this technique, you can still see them. Good, so we are talking about the interaction of electrons with specimens through light. An important aspect of this is how much the electron can interact with the light, okay? So I don't want to go over all these details. It's just to show you that we have been analyzing lots of different types of structures, types of optical modes that you can have, and then how much the interaction of electrons with those modes will be. You have, for example, 3D polaritonic structures. This includes plasmons, photopolaritons, whatever, anything that is a structure in 3D, or dielectric cavities, what I showed you before, these Mie spheres, etc. No? Or 2D materials, where you also can have very, very extremely confined polaritons, or even atomic systems. I will show you an example of atomic systems, or also dielectric lights, one-dimensional dielectric waveguides. So you look at the numbers, and after doing a lot of optimization, the percentage of electrons that have experienced an elastic interaction is going to be very small, typically very small. In electron microscopy, any electron loss spectra will typically show probabilities that are integrated in the losses, 10 to the minus 2, minus 3. Eventually, you have these waveguides where you have 600, okay, 6 photons per electron, right? So we are very excited about this. I think this can be a game changer in all this business. I will elaborate a little bit more on that later. So this is the diagram I showed you before. You have a waveguide, the electron running parallel to a waveguide. So the interaction time can be very, very long. And so that means the probability that the electron will excite a photon, or if there are photons here under the right phase matching conditions, that there is going to be absorption of the photons by electron, can be very high. No? That's what we are saying. This is not a big surprise. I like to show this historic paper right now. This is the first experimental demonstration of surface plasmons. And this is was a very controversial paper at the time. We were solving some kind of controversy even. Now it looks trivial to us, but it's not at all. And so surface science was not so advanced. Ultra high vacuum had not been invented. So they had to use fused aluminum and electrons reflected on this aluminum to just collect a spectrum. So it's not really microscopy, it's just an electron beam reflected with very good energy resolution for the time and this type of electron energies. And you could see some features in the energy lost by the electron corresponding to the excitation of surface plasmons, part plasmons, but also multiples of those, okay? So the electron could excite more than one, right? So this was there already, more than the one excitation per electron. Now, if you have a waveguide and then you go with a very, very grazing angle, then the interaction length, the effective interaction length will be depending on the extension of the mode outside the waveguide. Typically, this is going to be, say, this is hundreds of nanometers, this is maybe less than 100 nanometer. If you divide by the angle of the order of 1 milliradian, it's 1,000 times more, the interaction length can be very large. This is very realistic in parameters in electron microscopes, in integrated photonics. Now you have to make this atomically flat, etc. That's another thing. No? But then we are theorists, so no problem for us. But then you get 6 photons per electron. Okay, that's the prediction here. We are interested in exciting very efficiently. And then we have been looking at other systems in which you can do this. So this is an old business already for us, but we were working in periodic particle arrays and how you have these lattice resonances. I think this is well known for several of you in this community. So you have light interacting with a periodic array. There is an analytical description of this type of systems. The dipole induced by light in each of these small elements depends on the external field and the interaction between the different dipoles. Because of the momentum imprinted by the external light, all the dipoles have to have this dependence. And then this analytical solution, and this analytical solution is just depending on the sum of the dipole-dipole interaction, right? In a nutshell, this is what you have. Now, there is an optical theorem associated with that allows you to express the reflectivity of this system in terms of the polarizability of each of the particles and this lattice sum. But this lattice sum diverges when the wavelength is, say, for example, for normal incidence, and the wavelength is equal to the period, okay? This is beautifully explained. Oh, it's not here, it's a shame, but this is in this 1907 paper, Lord Rayleigh, where he basically explained good anomalies for the first time, and then he showed that basically when the parallel wave vector is equal to k, the wave vector of the light, basically the interaction between the different dipoles are in phase. So interaction of this with this, this with this, this with this is just 1 over the distance, right? And the phase is, in all cases, 0, or multiple of 2 pi. So this diverges. Because this diverges, eventually you have, no matter how small your particles are, there's going to be 1 point at which this is 0, so you have perfect reflectivity, even if you have something very small. And this was connected at the time with holes because of Barnett. No, the reflectivity here can be 100%. The transmission through the holes can be 100%. And this is the work that we did actually during a sabbatical here with Mole, and that was very, very good times. And then we demonstrated that this could be done with any arbitrary small particles. Now we go to electrons. What we want is to make use of these lattice resonances to enhance the interaction. And so the idea here is the following. Instead of having lattice resonances for light, now you have lattice resonances for electrons. You also have those, right? And now you come with an electron beam. The electron beam is diffracted, remember, by Thomson, diffraction by lattice. Now you have light. Either the electron absorbs light or generates light. What happens is that then after it generates light, basically the energy of the electron changes. So also the direction of emission changes. Basically, at some point, it could be that the wave vector of the electron is is similar to the wave vector of the lattice. You change it in such a way that you place the electron in a resonance. As then what happens is the probability that the electron interacts with the photon, either absorbs or emits, basically there is one energy or one angle, or you have to vary something here, in which it diverges, okay? Interaction is infinite. For this, you need a very good lattice, okay? In the context of periodic arrays for light, the problem is always to fabricate those, right? Unless you do, for example, X-ray scattering. In this case, with electron scattering, is the atomic lattice, so it's a perfect lattice, no problem. So that's one way in which you could get interaction probabilities of order unity just by doing this. No, when your conditions are such that the diffracted beam after emitting a photon is grazing, then the probability is just boosted to above unity. It's a linear probability. Okay, so you don't know linear eventually. I don't know. It will be order unity. Now, we also looked at the atomic systems. So in the table I showed you before, this is from a paper that came immediately before this one, that is a recent one. So we've been looking at Rydberg atoms. And so Rydberg atoms that you can now trap and create in optical lattices. And then one property of the Rydberg atom is for very high numbers, principal numbers, the dipoles associated with dipolar transitions, also non-dipolar transitions, the quadruples, etc. All these numbers are very high. No? In particular, the dipole moment is very high as the principal quantum number increases. As a result of that, an electron interacting with a Rydberg atom will essentially interact with the Rydberg atom, change its state with a probability, and this is a non-perturbative calculation that is approximately 100%. Okay, right. The Rydberg atom, we have to think of with atomic numbers, principal numbers in the range of 30, 40, or something like this. Then the atom size is in the range of, say, half a micron. So it's big. It's a big object. Okay. So there is another range in which electrons could be used to play with this type of systems. And it has certain potential advantages. An electron beam you can prepare is a wave, so you can prepare in a superposition of two states. I should have explained here, but you can do that in electron microscopes in a more or less routine way with beam splitters. It's just you put a charge wire, and the electron beam is just split into two parts, no? Or just a grating. It has been done both ways. And then you have a two-path electron interacting with the same Rydberg atom in two different places. So it will have a superposition of two. If you can then destroy which-way information from the electron, maybe you can do with another grating, and then you just collect the electron, post-select, then you can prepare a superposition of different states, or you can also make sure that, like this case, no, an electron has interacting with one of the atoms, but you don't know which one of them. So you have a superposition of the two. So basically, by post-selecting the electron, by detecting the energy lost, then you basically prepare the system in a quantum superposition. Okay, you add quantumness to the system. It's a bit paradoxical, no? Because then normally you detect, then you destroy quantumness. Here is the opposite. By making sure the electron has lost a certain amount of energy, you don't know where it is, no? You don't know which atom, which position, etc. Okay, good. So we come to also this obvious possibility, which is in a wavelet like this, because you can have a large interaction length. Eventually, you have remember the overlap between the dispersion of the electron and the dispersion of the light, the guided mode. And when the two of them coincide, then you have, in this condition, you have matching. I mean, you have coupling. Here it happens for a certain energy. So that's the spectrum that one would expect from an electron traveling like this, and then say you detect one electron in this range, you know one photon has been generated. There is nowhere else where the electron can be generated, right? It cannot be photons outside because it violates. Okay, so this we postulated as an efficient single photon source because you can have, I don't know, 10 to the 9 electrons per second. The probability can be made order 1. And then this has been recently demonstrated again in the group of Klaus Ropers, where basically they have these microring resonators, an electron. The electron is detected with the energy loss, different energy losses, and then a photon is detected in coincidence. And then you have the time delay between the photon and the electron detection. You see that there is a coincidence here. So it's a single photon generator, right? Heralded generator. The electron can also lose 2 photons, 3 photons, and you have the generation of n equals 2, 3, etc. Fock states. No? So this is work in progress. You could make the electron interact with a waveguide like this, and then in a waveguide you can have, well, it can generate light one side or the other. No, the electron is perpendicular, so the momentum in this direction is all of it. No, it's a broadband momentum supplied by the electron. This is the calculated electron energy loss probability that shows you the position of the wave-guided mode in the waveguide, the probability that the electron couples under these conditions to the different modes, right? And you could, for example, could excite one mode here, one mode here, with certain probability. What happens if you measure one electron here? So you measure an electron that has lost some energy, but it's not deflected. It's just going straight. One possibility is that it has generated one guided mode here, another one here. The sum of the energies is this. The wave vectors compensate, so it's undeflected, right? And there's this other possibility, so it's this one, but it's this other possibility, but you don't know which one you have. Therefore, you have entanglement between two different possibilities. And then again, we argue that with realistic waveguides, etc. But this is theory, so it's simple. Then that you can have a good probability of producing entangled photon pairs, or in this case, polariton pairs. Good. I will give you an overview of different aspects of electrons interacting with photons and then going quantum. So this is a bit weird thing, but I like it, and I think it has great possibilities. Remember the spectrum I showed you? So you can have energy loss, typical energy loss. Energy gain you can have also. There are more experiments I can show you with energy gain. Energy gain can be, for example, from thermal excitation of a system. That's actually a way that people use to measure, relating this and this, measure the temperature of a system, right? Locally with nanometer resolution. But basically you have an electron energy loss probability. If you multiply that probability by the energy loss and integrate, you get the average energy loss, which is negative. If you integrate the probability, you get the total probability, the inelastic probability. So the electron comes, it generates something, it loses coherence, right? No matter what the energy is, it loses coherence. Now, there is a low frequency divergence in the loss probability. And this is easy to understand. If you have a small object and the electron is interacting with it, as the frequency gets smaller and smaller, so the wavelength gets larger and larger, the particle comparatively smaller, so zero interaction. So it goes to zero. If non-radiative modes or radiative modes, it goes to zero. But if the infinity is very, very large compared to your distance, your wavelength, no matter how small the wavelength is, it will interact with the object. It will interact. So there is a divergence, the 1 over omega. Okay? So you plug it here, multiply, so the divergence gets away. The energy loss average is 0, but the total probability is infinite. That's okay. Infinite coherence doesn't violate anything, no? Still physical. It's an infinite that is physical, right? It doesn't predict, as long as it doesn't predict unphysical observation. Now, if you have a temperature in the system, say you interact with bosonic modes, photons, plasmons, whatever, no? Then you can generate losses in the electron. So you populate from whatever you have at your temperature with the Bose-Einstein distribution, you populate, or the electron picks up energy, and then the probability is like this, okay, for energy gain. So you have to compensate, weight this with this thing, right? For the probability, this is the probability of inelastic processes, so you have to sum. For the average energy loss, then this is gain, this is loss, okay? And now these two cancel, so you still have the same quantity as before. But now this one goes like 1 over omega at small frequencies. So the gain diverges. And now the divergence is even stronger, right? It's even stronger. So then there is a dramatic effect, and that we have been trying to explore by just having, again, a coherent superposition of two electrons, of the same electron, the same electron in two paths. And so consider two paths that are passing at different distances from an object, an infinite object. If this is much closer than this other one, this will interact with the system, with radiative modes, in a different way as this one. So this will generate excitations with different probability amplitude than this one. Therefore, the two of them, you can't tell which way the electron is going. And if you just combine the two to do interference patterns, then you will see a depletion in the interference, right? But if the two paths get closer and closer together, eventually, if this distance is much more than this, then the two paths interact more or less the same. So the probability amplitude is more or less the same. When they are exactly at the same position, it's the same, but even when they are close, it's more or less the same, meaning that the coherence, here, basically you are dressing your electron with a bag of photonic states that you are creating, and you have the interference. So the conclusion is, by having this type of geometry, you can detect the presence of an object. Now, if you go to an object that is, say, metallic, at low frequencies, we are talking about, metallic means good metal, then it turns out that there is not any fundamental length in the system. Everything depends on the ratio of this length and this length, right? Once you assume that this is a perfect conductor, there is no length, absolute length in the system. So this could be kilometers, as you still detect. You have to face other problems, like you want to do interference, there are magnetic fields everywhere, etc. No? At the moment, we are trying to do this in electron microscopes with microns, okay? And see if it goes. Now, what I want to concentrate now is in ultrafast electron microscopy, and this has been emerging as a very powerful technique in the last 10 years or so. No? So now you send photons, interact with the electron, and now you make it in all of the previous ones. There is no time involved, right? And now here, by doing this, if you have photons coming from laser pulses in the femtosecond regime, then you can gain temporal resolution, first of all, because you can time the photons, you can time the electrons. But plus, you can also crank up the intensity a lot. So the interaction can be very large with electrons. So this was demonstrated by Ahmed Sebail, the late Ahmed Sebail, died a few years ago. He received a Nobel laureate from femtochemistry, not for this, but here we said that he wanted to get the second Nobel laureate, and the statistics was in his favor, apparently. There are some that have two, and yeah. So, and many that don't have any. So then you have the same as before for the electron, but now your source is going to be a photoelectron source, where you send a femtosecond laser pulse, and you know when the electron is coming. And now part of this pulse, you maybe with a different frequency, you use it to pump the system. So you can synchronize the optical pump and the electron probe at the position of a specimen. and then detect what happens with the electron. And so if the two of them are, for example, arriving at the same time, the field will be very strong. The electron will interact with optical modes that are evanescent. It's not in vacuum. Therefore, it can absorb and emit photons, right? Many photons. So this was surprising. So that was the first experiment that was published by them with the theory. And I put here the theory card, but yeah, we took the experiment from their paper. And so this was surprising because for the first time you could see that these peaks, inelastic peaks, were having order unity magnitude, right? Comparable to the zero loss peak, right? So basically, you populate the system, the electron comes, and it absorbs photons or emits photons, actually in a stimulated way, right? This is different from EELs, where it's spontaneous. So the electron emits a photon, for example, or creates an excitation in a spontaneous fashion. So we did theory for this. The theory agreed very well with just one adjustable parameter, just the intensity of the laser, nothing else, right? We just moved the light intensity to see what happened. And then what happened was that you could see for the different channels, different photons exchange, you could see these interferences. So this cut here is just this curve, okay? One specific one. But then you move the intensity, say for a photon that has emitted electron emitted 5 photons, then you have depletion, no? Zero, maximum, etc. The zero loss peak then is depleted, then maximum, etc. So there is this coherence in the system. This is very important because the electron remains coherent. It's a wave function. It interacts with electromagnetic field, and it remains coherent. It's a wave function. These are not inelastic processes. You don't transform this into a coherent mixture of states, where the electron and photons, everything is just separate and not interacting. Okay? So this is light intensity. This was done a few years ago, again, by Klaus Roppers. This is light field. That's why here is the cone, the other one is parabolas. And then he showed this, basically. I will tell you one consequence that this has, and he was the one identifying it very soon. But the theory for this one was actually very easy. So you have the electron with its wave function, and then the electron interacts with light. There are a few papers where this theory is described, but essentially what happens is your electron, very energetic electron, 100 keV, is just changing the wave function by just a multiplicative factor, and this is like a frequency comb or energy comb, right? In this energy comb, you can identify the frequency of the photons, number of photons that are exchanged, and for each photon, you have this omega divided by v for the vector. Remember the condition omega equals kv, right? Phase conservation. So for every photon energy omega, you have a momentum omega divided by v, okay? In reality, these coefficients actually depend on the strength of the field, optical field, that is traversed by the electron. So you just integrate this field, do the spatial Fourier transform, again, the omega divided by v, the spatial Fourier transform, and that gives you some coupling parameter that enters into this special function, and then the square of this is just this. So beta is the optical field. If you increase the intensity, you have this plot that matches perfectly well with the experiment, okay? Then remember that we dismissed, this is important, so I go back all the way. I don't want to go back to do that in my computer because I will destroy the communication with the screen. Maybe I shouldn't have done this. Remember we neglected this because this is very small. It's a small momentum, very, very small, okay? But what is a small? Okay, what is the meaning of small? So a small momentum means for a certain energy loss, the momentum is omega divided by v plus something else, small thing. No, this something else is just a correction. It has to be quadratic. No, this L quadratic with the number of photons. No, but it's very, very small. Now, to propagate over very long distances, small change in wave vector can have an effect. Okay, so for those of you who are familiar with the Talbot effect, the classical Talbot effect, you have a sum with an exponential that depends on L, and another one which is L squared. This is the Talbot, classical Talbot effect, but now with the time instead of the space. And then what you see is the wave packet. So this is the wave packet. Initially is just like flat here, and it just modulated a lot as you propagate over large distances. So this is basically the wave packet over an optical period of the light that you are using. And so the wave packet, which is initially something very broad in time, ends up being a temporal cone. Okay, and this temporal cone has a width eventually of all these wave function reshapes in the attosecond regime. So how to understand this? Intuitively, you have a wave packet that is very large, many femtoseconds, maybe hundreds of femtoseconds, with your generated with photo emission from your photocathode, and then you imprint the light. And now this one that is very, very broad in time, obviously is very narrow in energy, all of a sudden it becomes a frequency cone. But then different components move with different velocities, and so they start interfering. And in this interference is what you get this type of compression, okay, in the attosecond regime. Okay, so recently we have been speculating about how you can combine this with an electron microscope, so you can do a bit of reshaping in time, but depending on the position of a beam that is now expanded in a broad beam. And so you have your electron optics that allows you to focus, and you can do focusing in time and focusing in space. No? Focusing in time with still preserving atomic resolution, focusing in space down to tens of femtoseconds maybe in duration. Right. I don't want to extend too much. 5 minutes will be fine. More things about photons. You can imagine you have a film that is transparent to the electron and is opaque to the light, maybe perfectly reflected. Maybe this can be like a 20, 30 nanometer silver film or gold film or something with 200 keV electrons. They pass, like 90-something% of them, unaffected, zero interaction. But the light is totally reflected, over the skin. I mean, it's thicker than the skin depth. So the electron can absorb photons because now this is not free space. It's just not infinite waves, but half waves. So you violate this mismatch of energy, momentum conservation, etc. And then you can have energy changes in the electron, momentum changes. This is seen better in this other experiment. So for every energy change in the electron, every photon that is absorbed, there is a small change in the angle of the electron, the transmitted electron. No? So you can deflect the electrons laterally with light. And we use this to predict, ideally, you use some shape light, a structured light, maybe using a spatial light modulator or something, then you could, in principle, recreate any focal spot that you want with any desired shape, right? And eventually, well, there are some experiments where people have been trying to do this using a spatial light modulator to modulate the electron and eventually do some desired shapes. No? So this is an ongoing direction. So I will conclude with just two very small things. Yes. Yeah. So this is something we are very excited about because just you can also have interact. This is what I didn't tell you, but basically one photon cannot be absorbed by an electron in free space. We cannot be emitted. But how about two photons? How about the photon comes, it absorbs, and is emitted? No. Well, this is the Compton effect. No, Compton effect. So the inelastic light scattering. So remember the phase diagram of the light, the electron and the light, but you can also do like this. Light here in the cone, and you end up outside the cone, right? So this is inelastic quantum scattering that you can have stimulated if you use two lasers going like this. So you can have, the electron can just absorb a photon from here and emit it from there, right? And then that way you also can change the spectrum of the electron by quanta of the energy, the frequency difference of these two lasers. And by doing that, adding more things related to coil effects, etc. Eventually, you can also do shaping. In principle, under CW conditions, without the use of pulses, of light pulses. So that would be a desirable thing to have in an electron microscope, that you can shape the electron and create temporal combs, even with continuous wave operation, without having to count the electrons, etc. So again, we hope this is the proposal. So we see. And the other proposal is just how to get to the septosecond. Why not? No. So attoseconds have been already mastered somehow. No. And now the idea here is you have something that can be in the range of maybe 100 femtoseconds. This is what you can create by photoemission with femtosecond laser pulses, 100 femtoseconds. And then can you interact with light such that you reshape your electron into something that evolves into septosecond, right? You can think the other way around. You start with a septosecond, propagate backwards. This is what you need. Can you transform what you have into what you need by using light? No. And it turns out that yeah, you can. I think we believe you can, and then you can have this as you propagate the beam eventually with the right conditions for this beam. Then you have temporal compression down to the septosecond. This occurs as it propagates. Eventually, you are saturating the uncertainty principle. So we are going with basically at this point you have a Gaussian beam, for example, it's already saturated the uncertainty principle. You populate it with light, becomes super broad in energy, but still is long temporally. So the product of uncertainties becomes super high, but eventually it goes down to the septosecond, where it's again saturating this relation. So this is my current group. We have also Terry Odom, who's visiting now Odom, so in this picture. And then let's say Cruz Velasco. I show you results from him in this front. This septosecond is done by Xin Jin, who's currently visiting. He's a bachelor student, but very brilliant, together with Cruz, also Adamantios, Andre. Well, I don't want to miss anyone since this is recorded, but anyway, many of these people contributed to this works. Okay, so thank you very much for your attention, and I'll be happy to take any questions if there are any.
Thank you, Javier.
Before that, let me do some advertising of our widgets that are now fully operational. So these are things where you can calculate photonic things or electron things, and these are operational. So you can go with your mobile phone and do things. Okay.
This is in his webpage.
Yeah.
So thank you very much, Javier. We were late, so I know you want to go for lunch, so let's be quick. Guys, if you have any question, I encourage students, especially, to raise their hands. Okay, we have a student here.
I wanted to ask about this kind of modality probability of interaction between the waveguide mode and the electrons. Is this kind of the same setup that people use for electron acceleration, like Peter Hommerhoff and these guys from dielectric structures? Is this the same effect, or is this?
No, that's in their case, In their case, that's a different thing because they have a bunch of photons. Is not acceleration. You see, it's not that all of the photons will be super active. In their case, the efficiency per photon is probably very low, but they have many in supply, and they are also they are facing other problems. Basically, you have to have this phase matching condition. That's everywhere. So this is the same, but that's everywhere. And then they also have to make it such that the beam doesn't diverge. No, so that's one of the considerations for them, right?
Okay.
And that's remarkable work what they are doing. Yes.
More questions? Yeah, Luis. No.
Another student.
Thank you, Javier. Very nice. In one of the first videographs, you showed the electron passing by close to an ellipsoidal nanoparticle with illuminated by light. You were comparing theory and experiment, and there was a splitting, I think, in the experiment. There was a real one. I mean, the peaks in theory was just a single peak, and the other have a kind of a doublet. I don't know whether this is some experimental artifact or is there actually some kind of interaction between these electrons and photons that give rise to this?
Yeah, I'm not very sure about that. I think this is not my work. It's Klaus Roper's work, and I think this is something some saturation in the detector or something like this. Yeah, yeah. But I'm not sure. So. Yeah, I don't know.
More questions? Well, I had one. As you explain how the field evolves, you basically, something you showed is that the nano is lost a little bit, no? You started with nanoparticles, and then you show us that it is long dielectric waveguides that give you the strongest tapping. Is there any hope to go back to nano in this field?
I think there is. In a way, we were proposing this. There are some experiments ongoing for trying to realize this, which is basically going to nano and an attosecond simultaneously. I think this is for microscopy, but much of the field is inspired by or aiming at other things that are not necessarily doing microscopy, but basically using quantum things for, like for example, for sensing, this sensing through the coherence. So my what I would predict is that the both microscopy and quantum sensing and quantum physics in general will benefit from this field. In the future, is not totally clear whether the best setups for doing these things will be actual microscopes, or instead maybe some electron beam with a bunch of things that you operate on them, etc. No, so. But the reality is that you have I don't know how many microscopes, electron microscopes in the world. I think it's over 1 million for sure, but I think one of the major uses is for inspecting microchips in these manufacturers facilities, and so you have so many that that's the natural benchmark for. No,
we need to give them a good idea to move from the usual transmission electron microscope.
Yes, that's right.
Okay.
That's right. I think that will happen. Yeah.
I hope so. Okay, Ivan.
A very nice question. You are going to septosecond resolution. So what could be the ideal process, the dynamics that you want to observe?
Yes. So this is the other question. No? This actually we've been thinking with Klaus Ropers and I know a lot about this. So once you have attoseconds, what do you do with those? That resolution, no? So far, you see even the quotation of the Nobel laureate in 2023. There are not many things that have been done so far, right? It looks like there is a big gap, and then the next thing is going to the septoseconds, and then obviously you need the small things, no? In 1 septosecond, basically light moves like the distance between 2 hydrogen atoms or so, no? In a molecule, H2. So you need something that is very, very confined, very fast, there are not many things that can do that. No, maybe at core level excitations. For example, if you produce a K-shell vacancy, then the evolution in that range is going to be in the zeptosecond range. Only if the atomic number is above, I don't know, 30 or 40 something. Otherwise, not. Even the hydrogen atom, no, is slower than that. And then nuclei, I don't know. These are things. Also, it's a challenge, no? It's a theoretical challenge. I mean, experimental challenge, no? To get to that, make things man-made that are in that regime, no? Now, if you talk to the high physicists, of which there is, I think, a community here at the Autonomous University, maybe for them this is going to be pointless because basically they are always using timescales that are much smaller, etc. No? So maybe, I don't know, depending who you ask, this can have a meaning or not. Yeah.
But it's no longer condensed matter physics, no?
Well, yeah, but yeah.
Okay, so if there's no more questions, let's thank Javier again for his talk.
Thank you.
And thank you all.